everybody for coming. The second to last lecture. So in the previous lectures, we have been discussing the simplest example of bootstrapping, which was talking about a single correlator of scalars. So if you call phi a scalar operator, we were talking about this 4-point function, and we wrote it as a sum over OP coefficient squared, labeled by scaling dimension and spin. And then the main thing we use is the fact that you can expand this 4-point function by rearranging the operators. This is Euclidean CFT. And so instead of expanding it in this way, there's a different expansion where basically these conformal cross ratios of your function's positions, they get switched. So you have VU instead of U and V. And so you could equivalently write this, instead of like taking the OP like this, you could also take the OP like this, which in particular is just switching 1 with 3. So you could write that in the alternative way. So basically with 1, 3 switched. And then equating the 1, 3 switched version to the original version gives a function's worth of constraints. Because you just have a different conformal block function here, and so you're trying to get constraints in the OP coefficients of scaling dimensions, and you have like a sum of these unknowns times this known function equals the sum of the same unknowns times the same known function. And that's what we leverage in order to get bounds on the scaling dimensions and OP coefficients. So in today's class, we're going to generalize this in the most basic way, which is very important, which is to talk about theories with a global symmetry. Because in the previous lectures, we basically weren't assuming any global symmetry. Although in practice, you could say Z2 symmetry. But assuming no global symmetry and assuming Z2 symmetry is actually identical if you're just considering a 4-point function of identical scalar operators. But I mean, the problem with just having such a general setup is that it's a bit too general. So like if you look at the bounds, the Ising model turned out to lie right on the boundary, which was nice. But there's like a million other CFTs you might want to study, and like they're just going to be somewhere within the allowed region. And so it's going to be hard to kind of like learn anything about them. So if you want to learn about other CFTs, you might as well put in the information you know about those CFTs. And because the approach we're taking is axiomatic, we don't want to put things that involve like the Lagrangian. We want to put kind of like non-perturbative facts that are definitional to the CFT. And the global symmetry is one of them. And so that's why it's very important to understand how to do bootstrap in the context of a global symmetry. So that's what we're going to do first. And then after we do global symmetry, we're also going to generalize to looking at 4-point functions of different operators instead of the same operator, which is another natural generalization, because of course, CFTs have different operators. Okay, but let's begin with global symmetry generalization. So we're going to consider a global symmetry G, and then we're going to consider a complex scalar operator, which I'll call phi I of x, where I is the index of some representation R. So R is an irrep of G. And phi is in general a complex representation. And so
G is any of the algebra.
Yeah.
Semi-simple algebra.
Yeah, any compact Lie algebra. Yeah. It doesn't even have to be semi-simple. I mean, it could have U1 factors. It's any compact group. You can even in principle do non-compact, but that'd be a bit more complicated. So let's just do compact. So basically, you just kind of go through and you repeat all the kinematics that we did in the previous lectures, except now, allowing our field to also have a label for this global symmetry. So for instance, the most basic quantity is the 2-point function of this phi. So we have a 2-point function of phi x1 and then phi x2. Let's put a conjugate, and here this is in the conjugate representation. So I'll give it label J bar. And so this 2-point function, you can normalize it so that it's very similar to the 2-point function we had without a global symmetry. Basically, the only difference is that now this is Kronecker delta saying that I must be the same thing as J bar. And so, I mean, this is not surprising because this is, after all, the only tensor you could write down with an index I and J bar. So this is how you write down the 2-point function. In fact, I mean, you can also write down 2-point functions for spinning operators, which is basically almost exactly the same as it was for the no global symmetry case, so I won't repeat that. The first interesting generalization is for 3-point functions. So recall, a quantity we always consider is a 3-point function of two scalars and a spinning operator, because this is kind of the natural thing that shows up in this 4-point function. We say the internal operator is spinning and the external operators are scalars. So now we're allowing this to be in some representation, the usual label I, j bar, and then there's the internal operator, which I will assume is in some representation R with label A. So like A is a label for some representation R of G. So this is in some representation, and so this R has to appear in the tensor product of the representations of the external operators, we call capital R. So if you look at the tensor product of representation capital R with its conjugate, then this little r has to appear in it in order for this to be non-zero. So otherwise the 3-point function would vanish. Okay, so this has a spin L. And so this is very similar to the definition we had in previous lectures, except there's now a tensor structure, and also you label the operator by its representation, which is this little r. And so at the bottom, we have the various position dependence, which I won't repeat because it's exactly the same as in the non-global symmetry case, so you can just look at the notes from what was there before. So I'm not going to repeat the position dependence. The main novelty is that there's now a tensor structure, T, which is for this representation. So there's I, j bar, and there's A. And then we put little r basically to label it. So this is some tensor structure with 3 labels, I, j bar, and A, which are the 3 labels on the left-hand side. And so this is fixed by group. And so in particular, there could be, in principle, multiple tensor structures for a given representation. Although in the simplest cases, there will just be one tensor structure and the 3-point function for given representation. But if there were multiple tensor structures, there'd be multiple OP coefficients. One for each such tensor structure. So now there's some basic facts which kind of immediately follow from group theory about the reality properties of this OP coefficient. So all the representations R that appear in capital R cross capital R conjugate are either real or they come in complex conjugate pairs. So that means we can choose a basis of this tensor structure T here such that these OP coefficients will satisfy some simple reality properties. So lambda phi bar O delta L R. So this guy equals, we can choose a basis such that this would equal the conjugate. For now it's phi bar phi O delta L R bar. Which you could then rearrange these labels. So instead of having phi bar phi, you could put at the cost of a -1 to the spin factor, you could write this as lambda phi bar O delta L R bar. And so this is a reality property that these OP coefficients satisfy when you have a general global symmetry. And so in particular, if the representation little r is real, so then the OP coefficient would be real when the spin is even, because then this is just the same thing as its conjugate, and it would be pure imaginary when the spin is odd, because when it's odd, then you have a minus sign there. On the other hand, if representation little r is complex, then the OP coefficients would just come in complex conjugate pairs. Okay, so this is one 3-point function which we consider. Another 3-point function which we can write down, which we'll also use in a moment, is the 3-point function. Instead of writing phi bar, we could also write phi j. So now both phi's are like, they're not conjugate, so just phi and phi instead of phi and phi bar. And then again, some operator OA, where now A is in some rep, which is in the R tensor product R. So this is just another 3-point function we can consider. And I won't write all the position dependence again, just for simplicity. So I'll just write the fact that you have an OP coefficient, and then there's a tensor structure, where now the labels are I, J, and A, instead of I, J bar. And then there's various position dependence. which is analogous to over there. And then, of course, you can also write the conjugate of this, where it'd be phi bar operator. And of course, in that case, A would appear in R bar across R bar. And so in this case, the reality properties, so you can choose a basis of these T's such that lambda phi O delta L R is the same as the conjugate of lambda phi bar O bar delta L R bar. And so in the case where you have these kind of identical operators, now this is a bit more analogous to the non-global symmetry case in that, so if this representation little r, so A is a label for representation R. So if R is in the symmetric product, or the anti-symmetric product of this tensor product R cross R, so if it's in the symmetric product, then you can choose this basis such that L must be, such that the spins must be even. And if it's in the anti-symmetric product, then with the same basis, L must be odd. And so these are all just some, kinematic generalizations of the statements we had previously when we didn't have a global symmetry. In that case, the spins were just always even. And that was kind of the trivial version of this more general situation where now that you have a global symmetry representation, for these 3-point functions, the spins are either even or odd, depending on if the representation is in the symmetric and anti-symmetric product. Whereas for this representation, you have both even and odd spins, and instead the OP coefficients just satisfy this reality. Okay, so that's the kinematics of 3-point functions. I'll do the kinematics now of 4-point functions over here. And so let's first write the 4-point function of scalars using the same labels in this configuration. X2, IK, X3, and IR, X4. Okay, so as usual, we have this X12 factor out here, this X34 factor. So the novelty, so before we had the usual sum over scaling dimensions and spins. Now, we now have representations R that are showing up in the OP of phi with phi bar. So they have to be in the tensor product of R with R bar. And now, to take into account the global symmetry labels, there's going to be a tensor structure labeled by R, which will have the various global symmetry labels. Okay, L bar. Then we have the OP coefficient modulus squared, phi dagger, O delta spin R, as well as the conformal block. So relative to the expression that we had without global symmetry, the main novelty is that we now are just summing, the operators are labeled by the representation R. These are any representations that appear in the tensor product of the representations of the external operators. And so you have to additionally sum over those representations. This is always a finite sum. And then you have a corresponding tensor structure for each representation. And the fact that you can write this as the modulus squared just comes from the reality properties in this case. So like the fact that this OP coefficient, you can write its conjugate as such. So this is one configuration. Now, there's a different configuration. And so here I should note that these spins can be even or odd. As explained on the other board. So the same 4-point function, we can write it in a different configuration. And so these things have to be equivalent, but at intermediate steps, it has some interesting differences. So now let's write this as, instead of having phi bar, let's write phi and phi. And then phi bar. So this is K bar, and this is phi bar. And so again, we have the same external factor. Usually sum over scaling dimensions and spins. So now it's the tensor product of R with itself instead of R with R bar. And so there's a different group theory structure here. I, J, K bar, L bar, because these are also different representations, because one's R with R bar, one's R with R. And so then we now write, and these are also different OP coefficients. So OP coefficient in phi with phi instead of phi with phi bar. Okay. So this is just rearranging these operators. So these things in principle have to be different, but it's just interesting to write. Like basically it's like, I'm assuming you're always taking the OP like this. And so the statement is just that these OPEs naively look different because this includes representations in R cross R, this includes representations in R cross R bar. Now, once you use crossing, you will equate these two guys.
Yes.
And so, but before you do that, I just wanted to emphasize you get different operators and different representations in each channel. So this is in contrast to the no global symmetry case, where it didn't matter which OPE you took, because you didn't have a representation label, you were always just getting the same list of operators.
Yeah,
Here, actually in each channel, you're getting a different list of operators.
Yeah, but I can fuse, for instance, x1 with x4 and x2 and x3, and I will get the same.
Sure, yeah, well, of course, yeah, because look, of course, these sums at the end of the day have to be the same. That's what crossing tells you.
Yeah.
But what's just interesting is that before equating them, these are sums of actually different operators.
Yeah.
So it's a bit more novel than the non-global symmetry case where even before you equated them, it was at least the same operators. So that might be.
Does it give you some interesting trivial relations?
It does. It indeed does. Okay, so before we talk about the crossing relations, we'll talk about those in a moment. I just wanted to comment that remember in previous lectures we spoke about a local CFT. So a local CFT was defined basically as a CFT that had a stress tensor, T mu nu, and so this was one operator which was like guaranteed to exist. So there's like this dimension D spin 2 operator which has to exist in any local CFT. And I also mentioned how you in principle could also consider non-local CFTs, which would still satisfy all the bootstrap constraints, and they would in fact appear in your crossing relations, in your bootstrap bounds. So for local CFTs, now that you have a global symmetry, in addition to having the stress tensor, there's also another operator called the current. And so this is the current for your global symmetry G. And so as long as G is a continuous global symmetry, then you have a conserved current associated with it. Now, if G is a discrete global symmetry, then you would not have a conserved current associated with it. So this is only if it's continuous. So this is for G continuous. For instance, if it's ON. So for an ON global symmetry, you would have a conserved current. And so then this guy has dimension D minus 1, and it's spin 1. And so this is another operator which is guaranteed to exist in a local CFT if you have a continuous global symmetry. And so with the stress tensor, we spoke about how there's a sort of canonical normalization of the stress tensor. Like that's the stress tensor you get, if you have some Lagrangian by taking derivatives in a certain way. And so for that canonically normalized stress tensor, its 2-point function was proportional to some quantity we called CT. And then if we instead, write our normalization of the stress tensor, which is not canonically normalized, but that's the one which has unit 2-point function, then in that case, the OP coefficient of our stress tensor, which we call, say, T tilde, so like if this was the OP coefficient of phi with T tilde, then this thing is proportional to 1 over square root of CT. And so this relation was useful because this allowed you to input CT into the bootstrap. Because the idea is that this OP coefficient is something that shows up, in your crossing relations. And so if you bound this guy, you're thus bounding CT. Alternatively, if you want to put in the value of CT, you can put it in by, dialing the value of this OP coefficient. And so there's an analogous situation now that you have a continuous global symmetry for this current J. So there's a canonically normalized J, whose 2-point function is proportional to something we call Cj. And then if we instead renormalize J such that it's unit normalized, then if we could take the OP coefficient, say with phi bar J tilde, and this will be inversely proportional to 1 over square root of CT. Very analogous to what we found here, and this can be derived kind of in an analogous way. Using the fact that you can write the charges that generate this global symmetry as an integral of this conserved current. So one detail though is that now that we have a global symmetry, we have to specify the representation of these operators. So this stress tensor, it's in the representation singlet. The conserved current, this guy, sorry, let's write that here. So this one is in the representation singlet. The conserved current, this guy is in the representation of the adjoint. And so the adjoint representation is a certain representation of the global symmetry group, which always shows up whenever you look at the tensor product with R bar. So that means the conserved current is going to show up in this configuration, but it will not show up in the second configuration. Because in the second configuration, the adjoint representation doesn't generically show up in the tensor product of R with itself. I mean, in some cases it does, but at least in the most general case, it's guaranteed to be here, not necessarily there.
Why can't the appear there to violate? Are you saying that sometimes R is equal to R?
Yeah, I'm just saying that there are, like in the most general scenario, the adjoint will always appear here, but not here. But there's also some cases where it also appears here. I mean, it depends on the specific group you're looking at. And
No, it's can only happen if R is equal to R bar.
Sure, yeah, if it's real, for instance. Okay, so this is just another quantity which you can bound and you can input into the bootstrap. Okay, so now let's talk about crossing relations. And so the crossing relations are going to be derived analogously.
And also stress energy tensor, it can be appeared in the above equation, not into the low one.
Yeah, I mean, basically you need the singlet to appear. And so again, you know, for a generic group, it would only appear in one, but for some representations, it could appear in multiple. Okay, so now we're going to talk about crossing relations. So crossing relations are derived very similar to how they're derived in this case. So we just rearrange the left-hand side, and that gives a different block expansion, and that's what gives you the non-trivial constraint. Now in this case, I had said that the only non-trivial crossing relation was where you exchange 1 and 3, whereas the exchanging of 1 and 2 was a bit more trivial, in that basically should imply that you can only sum over certain spins. But in this case, it's possible that both crossing relations could be non-trivial. So let's just take this 4-point function and let's swap 1 with 3, and let's also slap the labels I with k. And so we'll do that on this new board over here. So we take this 4-point function and we're going to swap 1 and I with 3 and k, which is another way of saying that we're swapping the first operator with the third operator. And so if we do that, in that case, we would get a 4-point function, which again has the form 5, 5R, 5, 5R. So that would have the same form as this first expansion, you know, but just with some of the labels mixed up. And so if you do that, you get a crossing equation, which I'll write here explicitly. So the representations are in R bar, because you get 5, 5R, 5, 5R even after swapping. So that looks the same. You get the same OB coefficients squared. You get, so here is the tensor structure before you swapped. This f is the crossing function, which I defined in the previous lecture, but I'll write the definition again in a moment. This is the thing basically we got from swapping the blocks. And then there's actually 2 kinds of crossing equations. So that's why I write plus and minus, minus, plus. You can get 2 different equations by either adding or subtracting this from its swapped version. So now this is the swap tensor structure. So it's k, j bar, I, l bar, f plus or minus, delta phi, delta l, u, v. This whole thing has to equal 0. We're here, this crossing function, so this is a very slight generalization of the crossing function we defined in the previous lectures. And there's 2 kinds, either plus or minus. So in both cases, we start with just the regular block times delta b to delta phi, and then the plus or minus basically comes whether or not we add or subtract the cross block. Okay, so this is the first cross equation we get, but you could also apply 1-3 crossing to this configuration, which would be the same thing, as Fedor said, as applying just a different swapping to this guy. So we could have also maybe swapped, instead of 1 and 3, we could have swapped 1 and 4. The point is, there's some other swapping which will relate a configuration which looks like 5, 5R, 5, 5R to one that looks like 5, 5, 5R, 5. And so that's kind of like the interesting new crossing equation. Because that's like of a different type than what we got in the case of no global symmetry. So this other crossing equation, so what's interesting is that it relates, you know, operators in different representations. So you're always summing over scaling dimension and spin, but now, first you have the operators that appear in R cross R. Because let's say we start with that being the original channel, So here we have these operators with their tensor structure, I, j, k bar, l bar. And then these guys are going to be related to operators in the other representations. So the representations that show up in R cross R bar. This -1 to the L is because we wanted to write this OP, we wanted to write an OP coefficient squared. And so like before you have the -1 to the L, it would have been lambda phi phi bar times lambda phi bar phi, but you can just make these OP coefficients the same at cost of a -1 to the spin factor. So this just makes it clear that this is a positive quantity. And then you have the tensor structure from the swap guy. So k bar j I L bar. Okay, so for each of these cross equations, there's always two kinds, either plus or minus. So you can either add or subtract this to its swap version. And then there's also two kinds of cross equations. One which relates phi bar phi to itself. The other one which relates phi bar phi to phi bar. And so these together give all the constraints from crossing. And so you can check as kind of a trivial exercise that if you had no representation, then this would just reduce to the single cross equation we got in the previous case. So in particular, you would only get something non-trivial from subtracting. Adding would just give you 0. And these would basically become identical. And so that's why you would just have 1. Okay. And so what's the next thing you would do in practice? So given a certain global symmetry, you would know what these T's are. So like these things is something you would work out, you have to using group theory. And so then this would basically be a bunch of equations where this T is some tensor. And so you'd want to solve for all the entries in these tensors. And after doing that, you could write like the solution in the following form. So like this would imply, these two cross equations would imply at the end of the day that you have some sum of operators labeled by scaling dimension spin as well as representation R. All of them are multiplying some positive OP coefficient squared, which is important for the bootstrap algorithm. But now you have a vector of cross equations. So that's what I write here, where this VLR, so I mean this is a function of U and V, and this VLR is just a vector whose entries are all going to be F's times various numbers. And so this is what you just get from like solving these equations. And by solving, I don't mean like completely solving, because of course that's what you're doing with the bootstrap itself. I just mean like solving for the various tensor structure entries. And so in the case of no global symmetry, this vector would have just been one entry, you know, which is what we got before. Now that we have a global symmetry, this is going to be a vector whose length is basically related to the specific representation of the external operator you're looking at. And so there's some patterns, but there's no like kind of complete rule. I mean, there's kind of like a rough intuition where like the length of this vector is like roughly the number of representations that appear on the right-hand side. But it's only rough, you know, because there's various exceptions. So it's like sometimes if a representation is repeated, that can change the number. So really you just have to work it out case by case. But kind of a rough intuition is that the length of this vector is growing with the number of representations that appear on the right-hand side. Okay. And so let's give an example, because this was a little bit abstract. And so let's give an example in the simplest possible case. So let's consider phi to be real. And our group G will let be the ON group, which is like the simplest compact group you could consider. So this is a real operator, and the representation of this operator will just be the fundamental. So that means I is just going from 1 to n. Okay, so this is very simple. And so if we're considering 4-point functions, we're going to have 4 of these phi's. And so we want to write down the tensor structures that were on the board hidden by this one. You know, tensor structures with 4 labels. So to figure out what those tensor structures are, let's first just write a basis of any tensor with 4 labels. And so it's pretty easy to guess what that basis would be, because you know there's not so many invariant tensors you can really write down for ON. So you would have delta I, j, k, l, and then you just have the 2 versions where you basically just permute these labels. So delta I, k, delta j, l, and the last basis element would be delta I, l, delta j, k. And so these are the only 3 ingredients you can have. So that, and also we know that if you look at the tensor product of the fundamental with itself, in the ON model, you just get the singlet, you get an anti-symmetric representation, which is the same thing as the adjoint. And then you get some traceless symmetric representation, which is usually called T. And so like the dimension of this guy is n times n minus 1 over 2. The dimension of this guy is n times n plus 1 over 2 minus 1, because you have to remove the trace. And then the dimension of this guy, of course, is just 1. Okay, so these are the only 3 representations you get. And so there's 3 tensor structures. And so if you want to compute the tensor structures for given representation, there's going to be various linear combinations of these 3 basis elements. And so there's various ways of working out what the precise linear combinations are. This is something which is described in the lecture notes, which everyone is studiously doing. So like in particular, you could write down the quadratic Casimir of the ON group and then just act with that on this basis. And then that would give you some kind of eigenvalue problem, and the eigenfunctions would be the linear combinations you want. Or there might be some other way. But just to give you the answer, so the tensor structure for the singlet representation, so that very simply is just this first element. So it's delta ij, delta k. The tensor structure for the antisymmetric representation, which is also the adjoint, so that's just the difference between 2 guys. I mean, it has to be antisymmetric, so there's pretty much only one choice. So minus delta. This is antisymmetric in the first 2 labels. That's why it's basically uniquely specified, up to some overall constant. And then finally, the last tensor representation for the traceless symmetric group. So here, you basically just symmetrize now instead of anti-symmetrize. So you start with delta ik, delta jl, and then you get the symmetrized version, which is delta il, delta jk, and then finally you subtract the trace, and that's what gives you minus 2 over n, delta ij, delta kn. And so as you see, n, the only place where n appears in the bootstrap is here. And that's the only place n is going to appear. So that's the only difference between doing different values of n, basically. And so basically, you would just take these explicit tensor structures, which I wrote down here, you would plug them in to these cross-union equations. Now, because it's the same expansion in both channels, in fact, only one of these cross-union equations, you only really need one of them, because the other one is basically equivalent. But okay, so you could take, say, the first one, plug in these tensor structures, and then just solve for the various entries, to get your vector of cross-union equations.
So you're saying that if I, rough speaking, take n to infinity, I know the solution. This is just a free large n model.
Sure.
And after that, I can study this as a perturbation.
You could, yes. Okay, so I mean, you could do large n perturbation theory, but that's like assuming a specific theory, like Owen Wilson Fisher fixed point. Here, I'm just talking about in principle any theory with Owen global symmetry, because the bootstrap is very general; it's just axiomatic, and so it's just saying any theory with an Owen global symmetry. We're not specifying Owen Wilson Fisher, and so the fact that the theory simplifies at large n, that's the case for Owen Wilson Fisher. I don't know if that's automatic for any theory which has a global symmetry.
Maybe this specifies for theory you want to study.
Well, yeah, but we're trying to be general. So we're just saying any theory with an Owen global symmetry. And so even when n goes to infinity, I mean, you still have 3 tensor structures. I mean, I guess this guy becomes 0, but you would still have. I mean, the 3 structures would still be independent.
Yeah, but still, I'm just saying that we know the solution to this situation.
But only for the Owen Wilson Fisher fixed point. I don't think you know the solution for any theory which has an O infinity symmetry. At least as far as I know. I mean, I'm not sure if there's some general argument that any theory which has O infinity, thus must be the O infinity Wilson Fisher fixed point.
Okay.
Yeah, I mean, you might be right. I'm just not sure. I'm just not sure if that's something which is guaranteed. Okay. So if you then just plug in these tensor structures, you work out the vector of cross-union equations. So first of all, this is going to be a vector with 3 entries, which corresponds to the fact that there was 3 representations appearing on the right-hand side. So this is kind of a simple example of the pattern where the number of cross-union equations is related to the number of representations, although it's not always such a simple correspondence. But anyways, so you have a different vector for each representation. So here's the scaling dimension. Here I write L plus to say the spins are even, because this guy, this is in the symmetric product, this is in the anti-symmetric product, and this is in the symmetric product. As you might remember from the previous slide, that operators in the anti-symmetric product, they have odd spins, operators in the symmetric product have evens. So that's what I'm specifying with this plus sign here. So this is even spins. This is for the singlet representation. I find this vector, which is 0, f minus, delta L, and f plus, delta L. Okay, so that's the vector you get for the singlet. For the anti-symmetric, now you get odd spins, so I write L minus. here, you get F minus delta L, F minus delta L, and F plus, with plus sign, delta L. And then finally, for the vector of crossing equations for the symmetric representation, so this has even spins again because it's in the traceless symmetric. So we get F minus up here, and then we get 1 minus 2 over n F minus, and minus 1 plus 2 over n F plus. And I won't write the rest of the labels for simplicity. And so the fact that n appears here is just inherited from the fact that n appeared explicitly in the tensor structure. But at the end of the day, like, it is these crossing equations which is what you're going to input into, you know, your programming software. And so you see that the only appearance of n is here. So the appearance of n is actually very, very simple. Okay, so hopefully this explicit example kind of demonstrates how things change once you have a global symmetry. But let's discuss, you know, in terms of implementation, how does implementation change? So in the previous lectures, we discussed for the case with no global symmetry, that the way you think about it is that you have some functional alpha, which is labeled by m and n, which is, you know, which basically corresponds to the fact that you have derivatives in terms of z and z bar of, you know, your crossing function f delta phi of u and v. So you were taking these various derivatives. This was labeled by delta and l. And so this was kind of the basic structure. Then you define some functional labeled by m and n for the number of derivatives, and then the number of constraints. You have like one constraint for every delta and every spin. And so we talked about how the way you can encode this is that you can write the derivatives of this crossing function as a polynomial in delta, and so then you could think of it as a bunch of constraints labeled by spin, each of which is a polynomial in delta. And then we discussed how semi-definite programming is kind of the natural way of implementing those constraints. And so how does this change now that you have a global symmetry? Well, the change is a very simple one. So basically, instead of just having a single crossing equation, you now have several crossing equations. You have a vector of crossing equations. So that means this function will have an extra label. And then this is just a label for which entry in the vector. And so let's call this label beta, where in this case, beta goes from 1 to 3. So the functional has an extra label because it needs to know whether it's not attacking on the first entry, the second entry, the third entry. But also, instead of, you know, just having a single crossing function f, we now have this v, which is like a vector labeled by beta, you know, for each entry. But we also have different v's depending on the representation. So that means the v's, instead of just having the label spin and dimension, as we had in the no global symmetry case, now they also have a label r for representation. And so the two quantities have changed. So our constraints have changed in the sense that the constraints have an extra label for representations, but also the functional has changed, that the functional has an extra label just for which entry of the vector of crossing equations. And so the way to think about this conceptually is that the more constraints you have, the harder it is to find a functional. If you can't find a functional, then you get an allowed point. And so you would think the allowed region would get bigger if you now have this extra label for the constraints. On the other hand, though, the more labels that the functional has, the easier it is to find a functional, because it means it's kind of there's like a bigger space of functionals. And the easier it is to find a functional, that means the more chances you get a disallowed point. And so that's what's kind of playing off against each other. So like the fact that the functional is bigger is playing off against the fact that the constraints are bigger, and that's why in general you just get a different set of constraints. You know, it's not automatically bigger or smaller than what you got without a global symmetry. And so that's why the change is non-trivial. But in terms of the implementation is pretty much exactly what we described in previous lecture. So I don't think there's even need to go over it again. It's just that you're now just going to be putting in a separate constraint for every representation. And the constraints will be vectors instead of just being, you know, a single constraint. But that's it. So at the end of the lecture, I will briefly go over the code again and demonstrate, you know, in particular how things change. But I'm just trying to say in words now that it doesn't change so much, because like really the only change is having this label there and the extra label for every representation. Okay. And also at the end of the lecture, I'll discuss some bounds you can get by actually bootstrapping now this ON vector model for different values there. But before we go into the explicit demonstration, let's also talk about mixed correlators, because that's the other important generalization relative to the single correlator case in previous lectures. So before we go on to mixed correlators, any question about this global symmetry case?
If I caught you right, you said that these two equations here in this case gave the same.
Yeah, because these two equations are kind of trivially the same, just because these two equations they came from writing the 4-point function in like 2 different ways. But if your representation is real, then these 2 different ways are actually the same.
Okay, that's what I was
Yeah. So like I was just trying to give the simplest demonstration of a global symmetry. Like, you know, more interesting cases will involve cases where the representation is actually complex, in which case it's not just trivial. Okay, so if there's no other questions, then I will move on to mixed correlators. So mixed correlators is another obvious generalization because, you know, CFTs have many different operators. And so why should you look at a 4-point function of just one operator? In fact, you know, conceptually, it might even be surprising that by looking at the 4-point function of just one operator, you would get any interesting values. Because you would think a CFT is, you know, infinite different operators, an infinite class of data you're trying to extract. Why is it by looking at just one quantity you get anything interesting? Now, it's surprising that you do get interesting things just by looking at one 4-point function. But it should also not be surprising that by looking at additional 4-point functions, you get even more things. And so this is why it's kind of like, you know, a very natural generalization. Okay, so let's consider now different operators. Phi. We're still going to make them be scalar operators. So that's the simplicity we use throughout these lectures. So now we have a little label I, which is just to label different operators. And each operator is going to be in some representation Ri. And so with the label I, capital I, this is the label for the representation Ri. But each of these operators could, you know, in principle, be in a different representation. Okay, so let's talk about the 4-point function. So now we have a 4-point function of different scalars. So this is phi I of x1. This is phi j of x2. This is phi k of x3. And this is phi l of x4. And so the first question is, before you even do a block expansion, how does conformal symmetry fix this 4-point function? So this is something you can just work out analogous to what we did in the first lecture, and you will find that it's like a slightly more complicated generalization. So in the single correlator case, recall that the dependence on x fixed by conformal symmetry is just this x12 to 2 delta phi and x34 to 2 delta phi. Now, when the 4 operators are different, this x dependence is a bit more complicated. So you have x24 divided by x14 to the delta ij, where delta ij is just defined to be delta I minus delta j. And then you get another x factor x14 over x13 to the delta kl. And then this is divided by the usual x factor. So delta I plus delta j, and then x34 to delta k plus delta l. And so this x dependence is basically what conformal symmetry fixes for you kinematically. Just translations, rotations, scalings, special conformal transformations. And then the remaining function, which we label by g, I, j, k, l, this function is just any function of u and v, where u and v are the usual conformal cross ratios. And so this is the generalization to how conformal symmetry fix the identical 4-point function. Of course, there will also be some tensor structure, which we are suppressing, which would take into account the various global symmetry indices. And so now, just as we did before, in the single correlator case, you can expand this general function g in blocks. And so this g, I, j, k, l, which is just, kinematically just any function of u and v, but by actually taking the OPE in this channel, so you're taking the OPE twice, you can see that this has a block expansion. So, generically there will be a representation. We've been kind of suppressing those indices. So you'll have phi I, phi j, O delta L R, then you'll have phi k, phi L, O delta L R. Then there's a tensor structure because it's global symmetry. And then there's a conformal block, but this conformal block is a bit different from the conformal blocks we dealt with before. And so in particular, it has labels that depend on delta ij and delta ko. And then as usual, it also depends on scaling dimension and spin of the internal operator. So this is a different conformal block from the conformal blocks we had over there in the single correlator case. And in particular, the difference depends on the difference of the scaling dimensions of the first and second operator and the third and fourth operator. And so if you want to do mixed correlators, you have to compute this more general class of conformal blocks. First of all, there's some simple identities which these conformal blocks must satisfy, which is kind of analogous to the identity for the single correlator block. So in the single correlator block, if you like swapped 1 and 2, then it had to satisfy some simple identity, which implies the spin must be even. So in this more general case, there's a slightly more general class of identities. So delta KL, delta and spin. So if you swap it such you get U over V and 1 over V, and this is the same thing as bringing out a factor of -1 to the spin, V delta KL over 2, G minus delta IJ delta KL. And all these things can be derived just by thinking about this as a product of 3-point function. -1 to the spin, V delta IJ over 2, and then the block delta L, UV, delta IJ, delta minus delta KL. Okay, so these are various identities that this mixed block has to satisfy. To actually compute the mixed block, you basically want to do exactly what we did for the single correlator block. So to kind of briefly review the argument. So the first way we discussed how to compute the single correlator block is that we wrote down a conformal Casimir equation. So we considered the generators L of the conformal group, we did some kind of square, and then we acted with this quadratic Casimir on the block. And because this is a quadratic Casimir, that means by definition it had to give some number times the block. And so this precise number depends on delta and spin. This is something you could work out using group theory. And then you could think of this quadratic Casimir squared as some kind of differential operator. And so this gave you a differential equation. And so solving for the eigenfunctions of this differential equation would give you these conformal blocks. But what we learned is that you could only actually solve this differential equation exactly when the dimensions were even. And that continues to be the case for the mixed block. So you can take the exact solutions of the conformal block in the single correlator case, say in 2 dimensions or 4 dimensions, and there's a very kind of straightforward generalization to the mixed block. So in particular, in the single correlator case, these blocks were written as a function of a hypergeometric function. So like you always had some function which looked like this 2f1 hypergeometric function. And the only difference between those formulas and this formula is that now you just shift these hypergeometric functions by delta ij and delta KL. And so just in the formulas from the previous lecture, whenever you get this hypergeometric function, you just shift the argument by delta ij, delta KL, and that gives you the mixed correlator block. But remember that when the space-time dimension is not even, then there wasn't an exact solution to this differential equation. So instead, you had to solve it basically recursively using Zalmazhkov recursion relations. And so in the mixed correlator case, you can just derive just the analogous Zalmazhkov recursion relations. They qualitatively are exactly the same. It's just that the coefficients in the recursion relation now depend on delta ij and delta KL. And so just an exercise of working out those coefficients. They're given in the lecture notes, and then you can just compute the blocks. But one kind of important, I guess, practical thing is that in the single correlator bootstrap, you only have to compute the blocks once for every spin. And so once you computed them once, you could just run the bootstrap as many times as you wanted. But in the mixed correlator bootstrap, because the blocks depend on delta ij and delta KL, that means if you're going to be scanning over like the space of various external operator scaling dimensions, you would have to keep recomputing the blocks for every new point. And so that's why mixed correlator bootstrap, takes a bit longer, just from that perspective, because you have to keep recomputing blocks for every new point. Thankfully, there's an extremely efficient block computing code called scalar blocks. This was introduced in the previous lectures, and that can, in a split second, compute blocks, for any, for delta I, J, K, or L. And so that's my practice. It's not an issue, but, historically, this was like a slight annoyance. So now we have the 4-point function expanded in our mixed correlator blocks, as defined here. We have this uglier X factor outside. And so the next thing we do as bootstrappers is that we just do crossing. So we swap the first and third operator or the first and second operator. And to get a set of Cross-check equations, which are very analogous to the Cross-check equations here, which we had in the global symmetry case. So it's kind of like a slight generalization of that. So in particular, let's start by swapping the first guy, which is 1i, with the third guy, which was 3k. So we're going to swap the left-hand side of this 4-point function and then equate it to its original 4-point function and try to combine all the various x factors into u's and v's. And so after doing that, So this it gives you a crossing equation as follows. So you have delta L and R. So you have the OP coefficient, lambda ij, O delta LR. Another OP coefficient, KL. So these letters in this case are just saying like which operator it is. So they're not group theory labels, they're just which operator labels. Then you would have a tensor structure, because we assume in general that, and I'm suppressing the indices for the global symmetry, because these IJKLs are just labels of which operator. This is delta J plus delta K over 2, and there's a conformal block, delta Ij, delta KL, delta L of U and V. And so this is, after swapping, equals some delta L R prime, basically the swap version. So now you have lambda Kj, O delta L R prime, lambda IL, O delta L R prime, and then the swap tensor structure, which all representations are prime in general, Kj, IL, and then a different factor of U, delta I plus delta J over 2, and then the swap block, delta L, delta Kj, delta IL, V, U. Okay. So this is the cross equation you get from swapping 1 and 3, for instance. And so the representations are here. These are representations that appear in the OPs of the first and second operator and third and fourth operator. So this has to be in the tensor product of, say, Ri with Rj, but it also has to be in the tensor product of Rk with Rl. On the other hand, the representations R prime, which appear after swapping, they have to just appear in now the swap representations. So Rk with Rj, as well as Ri with Rl. Okay, and so of course in general these will be different representations. So the set of representations R will be different set of representations R prime in general. And so so you now take this swapped equation, and you can either add or subtract it to the same equation, but just switching U and V. And so this is just a trick to get crossing functions. So if you take this and you add it to the same equation, but switching U and V, then you can write a crossing function, which is now written in terms of these f's, where the f's are the crossing functions we defined up there. So it's delta L R, lambda Ij, operator delta LR, lambda KL, operator delta LR, the tensor structure for R, Ij, KL, one of these crossing functions, which recall is just the difference between a block and its crossed version, except now these are mixed blocks, and that's why they have the labels Ij, KL, because the mixed blocks have those labels. Plus or minus sum delta L R prime, lambda Kj, O delta L R prime, lambda IL, O delta L R prime, tensor structure, Kj IL, and then this crossing function, Kj IL, x plus delta L. Okay. And so, as I just said, these f's are crossing functions which are very analogous to the ones that we defined before, I think on this slide. So before we defined, okay, sorry, maybe it's not here. It's fine all the way up there. Okay, so those are the crossing functions with identical operators. The only difference, now that we have mixed correlators, I'll just modify it here for simplicity, is that now we have these labels. So instead of just 1 delta phi, you now have the labels I, J, K, L, and basically you define this as delta K plus delta J over 2, and then this block itself has labels I, J, K, L. And then this U to the delta phi now becomes delta K plus delta L over 2. And this block again has labels I, J, K. So with that slight modification of the crossing function, these are the crossing relations you get in general, for any representation and for any generic 4 different operators. And so then, just as in the case of the global symmetry, what you do is that you would just put in the specific tensor structure that you get, and then you would work out some vector of crossing equations. But there's one big novelty between mixed correlators and single correlators, which is that, notice that we're not getting OP coefficients squared here. We're just getting products of 2 different OP coefficients. And so this is different from what we got over there, where naturally we always had OP coefficients squared multiplied by tensor structures. And so over there, and it's very important we have this positivity, because remember, an important input to the bootstrap algorithms, we have a positive number multiplying, some kind of like derivatives of blocks. And so using unitarity, we can assume that the lambdas are real, or maybe they come in complex conjugate pairs. But we can't assume they're sign. And so this lambda times that lambda, we don't know if it's positive. I mean, it could be negative. And so this is why, to take this into account, it's not sufficient just to write this as like a vector of scalar constraints. Instead, we want to construct matrices, which will be multiplying vectors of OP coefficients, and then demand that those matrices be positive semi-definite. So to make this clear, let me give an example. But the idea is general. And so this is why ultimately you want matrix constraints. And so this connects to the fact that in the previous lecture, when we were discussing implementation of the bootstrap, I gave kind of a general discussion where I wrote about how semi-definite programming can take into account matrix constraints, so matrices of polynomials. And so the reason why those matrices are useful is precisely because in this mixed correlator case, that's kind of the natural kind of constraint you get. Okay, but let's give an example to make this a bit more concrete. So let's consider all operators in theory with Z2 symmetry, which is the simplest possible case. And so we're going to have the operator sigma, which is Z2 even, or Z2 odd. And then we're going to have the operator epsilon, which is Z2 even. And we're going to define sigma and epsilon as the lowest dimension operator, which is either Z2 even or Z2 odd. So we want to consider all 4-point functions of sigma and epsilon. So there's not so many possibilities. So either you could have the 4-point function of sigma with itself, you could have the 4-point function of epsilon with itself, and then finally you could have this mixed 4-point function. So with sigma, epsilon, epsilon. You can't have anything else because that would be killed by Z2 symmetry. So you can't have sigma, 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 epsilon, for instance. And so we just want to now apply these, the formulas we just worked out to this specific case. And so in this case, the tensor structures are basically trivial because there is no continuous symmetry, it's just Z2. So the only novelty is the fact that I, J, K, and L are different. So in particular, in the first case, well, the first 2 cases are all the same, but in the third case, I and J will be the same, and only K and L will be different. So if you just apply that to these cross equations, so you take this specific crossing function, and you just look at all the different cases, so either I, J, K, and L are the same, or I and J are the same, K and L are different, and tensor structure is trivial. So then you find that there are 5 crossing equations. And so, and I'll explain why you get 5. So you get one crossing equation for this 4-point function, because this is just the usual single correlator 4-point function. So let's write this in the usual way as a sum over scaling dimensions and spins, even spins in particular. So remember, spins have to be even in single correlator bootstrap. So we have sigma, sigma, O, delta, L, and I'm going to write plus for the representation because this is in the Z2 even sector. So the representation is either plus or minus here. So it's very simple. It's either minus or plus for representation. And then we have this crossing function, which is just the usual single correlator. So I'm just writing sigmas here. And the fact that there's a minus here, this has nothing to do with the representation. This just has to do with the fact we define 2 different kinds of crossing functions, where you either subtract the block or add the block. And in the single correlator case, the one that is non-trivial is where you subtract the blocks. If you were to try to add these cross equations, you would just get 0. Okay, so this is the cross equation we get from sigma. From epsilon, we get the analogous equation. So it looks exactly the same, except now you have OP coefficients of epsilon instead of sigma. Delta L, again, this is in the plus representation. We get the same F here. Okay, so this was easy. Now let's move on to the new one. So first of all, we can consider the configuration sigma epsilon. So the idea is that we can consider configurations and then we always swap the first and the third. And that's just like one way of keeping track that we're doing all the crossings. So if you swap the first and the third, then you still get sigma epsilon, and so that just gives one crossing equation. So now the spin's gonna be even or odd, because you only have the constraint on spins when you have two identical operators. When the operators are different, the spins aren't constrained. And so we get this OP coefficient squared, sigma epsilon, O delta L, and now this is in the Z2 odd representation, so I write minus sign here. And then we get sigma epsilon minus delta L. And so now this crossing function is one of these mixed crossing functions, that we defined up there. So it's actually taking into account the fact that there's mixed blocks, unlike these two, which didn't need that. Finally, we could also consider crossing to this configuration. And so when you do crossing here, sigma epsilon gets related to sigma epsilon sigma. And so for this crossing equation, you can either add or subtract the swapped version from the original, which is the freedom of plus or minus there. And so that's why we get two crossing equations in this last one. So I write it as one equation, but it's really two, because that's how I put in a plus and minus. So first, you have the sigma epsilon configuration. And so that gives one OP coefficient for sigma. It's in the plus representation, and then another OP coefficient for epsilon, also in the plus configuration. And then we have two crossing equations, either minus or plus. But then this guy is added to the sum of operators in the other representation, i.e. the minus representation. So there's a minus one to the spin factor we get just by rearranging the labels so that we get an OP coefficient squared. Otherwise we would have had sigma epsilon sigma. And then we get epsilon sigma epsilon. So this is another one of these mixed crossing functions. Okay, and so this is two sets of crossing equations corresponding to the fact you would choose either plus or minus. This plus and minus is not to be confused with the representation label. Sorry, that's kind of bad choice of notation, but it's two independent concepts. So 5 crossing equations total, 1, 2, 3, 4, 5. And so as you see, these crossing equations were all written multiplied by a positive number, which is OP coefficient squared. So was this guy. The only thing which is not an OP coefficient squared is this first term, where it's lambda sigma multiplied by lambda epsilon. And so this is kind of the problem guy. This is why we need a matrix constraint. If we didn't have this guy, we wouldn't need a matrix constraint. And so we now want to, combine these 5 crossing equations into a vector of crossing equations. So like a 5-dimensional vector, because there's 5 crossing equations. But we'll have 2 vectors, one for the odd representation, one for the even representation. And so for the odd representation, there'll just be a vector of scalar quantities, because everything's multiplying OP coefficient squared. It's only for the even representation that we have sigma epsilon, and there we'll need a 2x2 matrix. Okay, so similarly write this out explicitly. I'll do that here. So we can write the crossing equation coming from those guys as, first of all, the simple equation, which is sigma epsilon. This is just a usual vector of scalar quantities. So this V is some 5-dimensional vector I'll define in a moment. This is for the odd representation. But then the more interesting guy is this matrix constraint. So lambda sigma O, lambda epsilon O, and then this is going to be a vector of matrix constraints, delta L plus, and then lambda sigma O, and lambda epsilon O. Okay, so as you see, this is a 2x2 matrix sandwiched between a vector, sigma, epsilon.
So do you assume that in minus and plus channels are the same operators?
Well, I'm not making any assumptions, but generically it will be different operators because they're different representations.
Oh, I meant like all of this O delta L plus, O delta L minus are the same. O delta L plus. It's just like for me, each of this equation, it's like it's separate equation. You cannot consider them.
Well, so these are different operators. The operators with plus, the operators with minus are different.
Yeah, but Mike, I meant the operator plot like in the first and the second line.
Yeah.
Right. These operators are different.
Well, no, in principle, could be the same operator could appear in both OPs.
Yeah.
Because, like, I mean, the OP is just saying as long as you have the right group representation, you can appear. And so because these are both in the even representation, the same operators could be appearing in here and here. Yeah, in fact, it's important that the same operators appear, because otherwise this matrix string would be trivial, because you wouldn't have any off-diagonal components. But yeah, so it's good to know that they can appear in both. Okay, and so what's the vector cross equations we get? So first we can start with the simple one, which was delta L minus. So this was just a vector of scalar constraints. So we have 0, 0, and so I'm just reading this off from there. So I'm just reading off what we wrote there, organizing this into these vectors. So I'm not going to write all the labels here for simplicity. F minus, epsilon sigma, sigma epsilon, and then finally minus 1 for spin, F plus epsilon sigma, sigma epsilon. Okay, so this was the first one. And then the second equation is a more interesting one. So this is the one which is a matrix equation. So again, you just read this off from what we have here, but writing it like this. So basically, wherever we have sigma sigma, it's going to be a diagonal. Okay, so for instance, the first term comes from there. And so you see there's going to be a 2 by 2 matrix where we're going to have sigma, 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 and then just zeros every rows. Because we only want to multiply lambda sigma squared. And then for the second term, we're going to get an analogous thing, except now we're only going to have this guy to be non-zero. This is going to be F, epsilon, 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 epsilon. Okay, so the third line is just a 2 by 2 matrix of zeros. And then finally, what's interesting is that for sigma, sigma, epsilon, epsilon, so from these last two equations, we're going to get terms that have off-diagonal terms. So we're going to get F sigma, sigma, epsilon, epsilon minus F sigma, sigma, epsilon, epsilon minus. And then similarly, same thing here, except F plus. That's the only difference between those last two equations. Sigma, epsilon, epsilon, F plus, sigma, sigma, epsilon, epsilon. Great. So the fact that you have off-diagonal entries is why you needed a matrix. Because of course, if you only had diagonal matrices, you could have just written this as this non-matrix constraints. And so the important thing now is that now when we implement this, so going back to our brief discussion of the functional, so not only are we going to have this label beta, which is for each crossing equation, but we're also going to have an additional label for, say, it's a matrix constraint. We're going to want to say like which entry of the matrix. So we'll have some like two labels. Let's call them like I don't know, A and B. Because the alpha is going to be acting on different entries of the matrix. V here, on the other hand, is not going to change aside from the fact that I guess they'll also have a label A and B, because it's like which entry in the vector, and then of that vector, which entry in the specific matrix. But we discussed in the previous lecture how semi-definite programming naturally handles constraints that are matrices of polynomials. And so this is naturally a matrix with matrix labels A and B of polynomials, which is derivatives acting on this crossing function, polynomial in delta. And that's something which is naturally handled by semi-definite programming, as we discussed in the previous lecture. And so that's why we can take into account even this general case where you have these matrix constraints. And so the idea is that you're looking for functionals which are going to be making these matrices positive semi-definite. Which is kind of the natural generalization of just merely demanding positivity. But okay, so before I go into the explicit demonstration in a moment, I just wanted to briefly go over some things. So like, remember that there's kind of three components to the bootstrap. So first of all, you have your list of constraints, and then there's some quantity you want to normalize, and then there's some quantity you want to extremize. Now, if you're normalizing a quantity, that has to be a scalar quantity. You can't normalize a matrix. And so this might be confusing, right? Because like previously we spoke about how in some of the algorithms you have like alpha acting on like the V for the identity. And this is being normalized, say, to 1, right? But the identity operator, say in our explicit example, well, that would show up in the even representation, because obviously it's Z2 even. And it seems like we have a matrix constraint. And so how can we be like normalizing a matrix to 1? And so the resolution is that for special operators such as the identity, you know what the OP coefficients are, so you can write the matrix constraint as just a scalar constraint. You know, just because trivially, you know what lambda sigma sigma identity and lambda epsilon identity is. So in particular, you know that lambda sigma sigma identity, you could just normalize this to 1. Similarly, lambda epsilon epsilon identity should be normalized to 1. And so then, you know, you don't need to write this as a matrix constraint specifically for the operator. You could just collapse this into a single constraint, one for each V, one for each entry of V, and that's what you're normalizing to be. So I mean, you know, to write this more explicitly, it's like you would take this matrix V and you would contract it with 1, 1, and 1, 1. And then this would give a scalar quantity, which is then, which can then be normalized. And so it's an analogous story for extremizing quantities. So like, you know, we spoke about in previous lectures how, you know, the way you bound OP coefficients is that you normalize, say, a specific operator, which isn't identity, to be 1 or minus 1. And so say, for instance, the stress tensor, you'd want to normalize that operator. And so similarly for the stress tensor, even though it starts off as a matrix, you know how the OP coefficients of the stress tensor, they're all related in terms of one quantity. So like in particular, lambda sigma sigma P has to be proportional to delta sigma squared over C squared CT. Or let me just write this as a square. This is something which we derived in previous lectures. And similarly for lambda epsilon epsilon. As well as their geometric average. And so this means if you're trying to extremize this specific quantity, you can again just collapse this into a scalar constraint, you know, by putting delta sigma, delta epsilon, this matrix specifically for the stress tensor, delta sigma, delta epsilon, and then this is now some scalar quantity which you can then naturally extremize. Okay, so that's kind of like the only conceptual difference. And so in the remaining few minutes, let me now connect to my screen. And we can so I'll share screen. Desktop. Bring the screen down. Okay, so we're now going to review some results. That we just described in this lecture. So the first thing we described is how to generalize the bootstrap to the case of a global symmetry. Is the thing still turning on? It's off. Oh, okay, so maybe we should just turn off the lights a little bit. So here are some bounds you get in the case of identical operators, but fundamentals of an ON global symmetry. So you can bound the lowest dimension singlet operator, which is called delta S, that's what's on the y-axis. On the x-axis is just the scaling dimension of the external operator, delta V, which is the fundamental. So this plot could be compared to the plot we discussed in the previous lecture, which was just for a Z2 symmetry. Now it's for ON symmetry, so you get a different upper bound for each n. The dotted guys are the ones you could compute using Docker yourself, just in like a minute or so. The solid lines is with more derivatives, just to kind of show how things are converging. And the interesting thing is that these black dots, as well as this gray dot, are kind of predictions from other methods. So in particular, for the black dots, I think that was computed with Monte Carlo, where people did lattice Monte Carlo studies for low n. The gray dot instead is computed from large n, because this is for n equals 10, so this is where you expect large n to be valid. And what's interesting is that you find a kink right where these other predictions were for the Owen-Wilson-Fisher fixed point. So this is kind of like the generalization of the Z2 Ising model results from the previous lecture now to the case of ON. So it seems like in general, Owen-Wilson-Fisher fixed points, where n equals 1 is the Ising model, always lie at some special point on the boundary of this allowed region. And this is something you could only learn by inputting ON global symmetry. Because the bounds from the previous lecture, in principle, they applied to ON global symmetry, because they applied to any symmetry. It's just that these special points would have been somewhere in the allowed region. And so in order to get more constraining bounds, such that the theory is now on the boundary of the allowed region, this is why you wanted to input a global symmetry. Okay, so this is kind of an interesting fact about the bound of singlet versus external. You can do an analogous bound for the traceless symmetric representation, which also contains even spin zero operator. It's a little bit harder to see, but there's also a kink, which is also where Monte Carlo or large N predicts the values of these theories to lie. So one perhaps subtle point is that, of course, ON plus 1 includes the group ON. And so thus you would expect the bounds from ON plus 1 to kind of be like stricter than the bounds from ON. And so for the traceless symmetric, that's indeed the case, where you see that like the purple bound is stricter than the red bound, which is stricter than the blue bound. So 10 is stricter than 3, which is stricter than 2. For the singlet bound, though, it had the opposite order, where it seems like 2 was stricter than 3, which is stricter than 10. So this is a little bit confusing. The resolution is that you have to be careful what you mean by traceless symmetric and singlet as you're changing N. Because the traceless symmetric representation of ON plus 1, once you decompose it to ON, will include both the traceless symmetric as well as the singlet. And so that's why you just want to compare like the lowest dimension of either singlet or traceless symmetric of ON to the lowest dimension of either traceless or singlet of ON plus 1. And then they are inclusive in the right order. Okay. But like that's kind of an example of something in general with bootstraps could be careful about, is that because you're only putting in very general things like the global symmetry and like that's it, thus literally any theory with that global symmetry can show up. It's not guaranteed to be the specific Wilson-Fisher point you care about. And so that's why you really have to be careful about kind of like weird things like, maybe a different theory, but like a certain, subgroup of its representations or stuff like that. Okay, so this was the story for an example of a global symmetry. So now I can show example of what you get from mixed correlators. So before I show these results, one conceptual point is that if you do this mixed correlator setup, and if you don't impose any gaps, so remember in the first lecture we discussed a gap is where you say that like all operators are dimension 3 and higher, except for one specific operator I'm putting below. And so remember in the previous lecture, we discussed how just with the single correlator, by putting in a gap on delta sigma, you could get kind of a peninsula allowed region. But it wasn't an island, it was more of a peninsula. So if you don't put in any gaps and do mixed correlators, you gain nothing. So what do you gain by doing mixed correlators? What you gain is that you get access to operators you didn't have access to before. So in the single correlator, when you look at delta sigma, when you looked at sigma, 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 you only got Z2 even operators. You didn't have Z2 odd operators in your block expansion. Because even times even is always even, or odd times odd is always even. So the advantage of doing mixed correlators is that you now have these Z2 odd operators in your spectrum of operators. So that means you can now impose a gap both on Z2 even and Z2 odd. So the advantage of mixed correlators is that it allows you to impose gaps on a wider selection of operators. And so in particular, if we want to look at the Ising model, we should say that there's only one relevant operator, which is either Z2 even or Z2 odd. And so now if you put those gaps in addition to doing mixed correlators, which is what mixed correlators allow you to do, that's what gives you this nice island. So as you see here, these are plots which I computed using Docker, so you can compute them yourself, using just the mixed correlator constraints that we just derived in this lecture. And so the novelty here is that unlike in the previous lecture where we got some kind of peninsular region, now we actually get an island. So these light gray dots are the dots that are disallowed, and the blue dots are the dots that are allowed, and as you see, it's just an island of an allowed region. And so what's nice about this island is that, first of all, this island is showing up right where the kink was. So in particular, this red box is where Monte Carlo predicts the theory should be. So the right-hand plot now zooms in, and as you see, and this is also with higher derivative order. So this is a slightly more converged plot on the right-hand side. And as you see, the island is converging so that it is, getting within the red box predicted by Monte Carlo. And so these are just some plots I just created in like a few minutes using Docker, just to demonstrate, how feasible this is. So this is something you will do, if you're doing the problem sets. Of course, since then, people have went to much higher derivative order, and they've included, other inputs, which have allowed the island to actually get much, much smaller, such that it's actually significantly smaller than Monte Carlo, and in fact, it's within the Monte Carlo box. But this is just kind of a demonstration of what you could do, you're using the things we discussed in this lecture. So one last comment I'll make about mixed correlators is that there's kind of like a couple simple tricks you can do in order to improve your bounds. So the first trick is that in these crossing equations we wrote down, we had lambda, sigma, epsilon operator and lambda epsilon epsilon operator. But that operator in particular could be sigma or epsilon. So for instance, if we're looking at the Z2 even sector, it could be epsilon. If we're looking at the Z2 odd sector, it could be sigma. And so lambda sigma epsilon sigma and lambda sigma sigma epsilon are both showing up. But of course, these should be the same quantities because you should be able to permute the labels and they should be completely equivalent. But this is something which so far we didn't impose. So, but it's something you should impose and it just gives better constraints. So in particular, here what's demonstrated in this equation is that you take the matrix constraint for spin 0 in the Z2 even sector, so which involves sigma sigma epsilon, and you use the fact that that should be the same thing as sigma epsilon sigma, which appeared in the Z2 odd sector. And so instead of having two separate constraints in this specific spin 0 sector, you should just combine this into a single constraint. And so this is guaranteed to give more constraining bounds. Because basically now you have fewer constraints, which means it's easier to find a functional, which means the disallowed region gets bigger. So that's one improvement you do when you do mixed correlators. The second improvement, which is more significant, is that so far, the bootstrap doesn't know that there could be many degenerate operators which all have the exact same scaling dimension. So like, we've imposed by putting gaps up to 3 that there's just one relevant sigma and one relevant epsilon. But how does the bootstrap not know that there's 50 operators called sigma which all happen to have the exact same scaling dimension? So physically, of course, we know that's crazy. But this is just a stupid algorithm. It doesn't know anything except for what we tell it. And so far, we haven't told it that's not the case. And so we want to tell the bootstrap that there's a unique operator of dimension sigma and a unique operator of dimension epsilon. And so the way to do that is that instead of just having a matrix constraint, for sigma or epsilon, you could, and so this matrix constraint is a matrix, multiplying, sigma sigma epsilon and epsilon epsilon epsilon. And so if you want to impose that there's just a unique operator, you basically want to scan over all possible values of those OP coefficients, because this is basically ensuring that there will only be one operator multiplying these OP coefficients. Because if there's multiple operators, then like putting in these explicit values, would kill that possibility. And so this is just a bit more expensive, because this means that instead of just scanning over the value of delta sigma and delta epsilon in some kind of 3-dimensional plot, you would also have to be scanning over like the angle between their relative OP coefficients, which is parameterized by this theta. And so this is something I didn't do in the plots shown here for simplicity, but this is something which, if you're doing a more sophisticated bootstrap, you would do in order to further make the island small. Okay, so I think we're just around the end of time. It's 3 o'clock. So that's the end of the conventional lectures for this course. So to kind of recap, we started by introducing the constraints of conformal symmetries in kinematic sense. We discussed dynamical constraints, so unitarity bounds, and other things you learn by having a certain quantization. We then discussed how to set up the bootstrap, first for single correlators, and now in this lecture for both global symmetry as well as mixed correlators. We also described how to implement this using SDPB, particularly using this Docker software, so it's something you can do at home just in a few seconds following the lecture notes. And this culminated in getting islands for the Ising model, which we know correspond to the Ising model because, in fact, they overlap and, in fact, are even more precise than Monte Carlo predictions for those. And so in the next lecture on Wednesday, which is the final lecture, that will be talking about the future of the bootstrap. So it's going to be kind of a general overview of what I think are the most significant results of the numerical bootstrap to date, and then followed by targets for interesting bootstrap problems in the future, which hopefully you guys can help figure out. So that's why I encourage people to show up for the last lecture, even if you haven't shown up to any of the lectures before. The last lecture will be kind of an independent thing. Thank you.
I had a quick question about the gaps that
Sure.
you're assuming. Is it clear, like just from where you started analytically, that delta sigma will be less than delta epsilon? Is that right? That ordering, or is that just come out of the bootstrap? Like,
Okay. So that's a good question. Is that like it seems like the way delta sigma and delta epsilon are entering, they're kind of entering on kind of like equal footing. So it's kind of like look, I mean, in principle, one is supposed to be Z2 even, one is Z2 odd, but in terms of these cross equations, you're like, at least in these cross equations, you're not really seeing that fact. It's like I could have told you that epsilon actually is Z2 odd and sigma is even. So in practice, you're just saying that there's two relevant operators, one which is in one sector, one which is in the other sector. But they are in different sectors though. So like in the plus sector, there's just one relevant operator.
And so that's why, you know, it's kind of meaningless to say like, oh, which dimension is bigger. I mean, it turns out one is bigger than the other, but they're in different representations. And so that's why, you know, you don't have to worry about them.
Well, I guess I was just wondering, is there an argument, even before you started the bootstrap, was there an argument that one had to be heavier than the other, or this is something that just comes out?
Okay, so I think there's some kind of intuition where it's like delta epsilon is what's sometimes called like the energy operator. It was like the lowest dimension singlet. And so I think that tends to be higher dimension than sigma, which is what's called like the order operator. So like in condensed matter, you know, studies, like epsilon is usually kind of corresponds to like how many things you had to tune in the UV in order to get to this point. And so that's kind of like the first thing people measure. And then delta sigma is like the second thing people would measure that would be related to some kind of like susceptibility or something. And I think in most cases delta sigma is smaller than delta epsilon. But like I don't know if there's like some theorem of why that is. Yeah, I think that's just in every case.
And then bootstrap proves it.
Yeah. So okay. So like I mean, and another thing I should comment is that in the first lecture we had this kind of question of like, why do you have this concept of universality? So like, why is it that like many different things, you know, like, you know, bottled water, you know, the Ising model, magnets, like why do they all end up being described by the exact same theory in the IR? And so I said that like the way you prove that ultimately is that you show that with the assumptions of a certain symmetry, say Z2, and a certain number of relevant operators, say 2, there's an extremely small class of theories that are allowed by those constraints. And so hopefully it's something you are now convinced through, because the bootstrap proves that only with those assumptions of Z2 as well as number of relevant operators, you find a tiny allowed region. Everything else is allowed. And so this kind of proves universality. And so I would say prior to the bootstrap, the statement of universality was more of a conjecture than a proof, because like we didn't know why there were so few CFTs, you know, with these constraints. But like now we can actually show it.
I still don't know, maybe it's like, you know, there is a huge region.
Sure, yeah. So it's not a complete proof, you know, because, you know, this is an island, but like far away from the island, there would still be another allowed region. You know, so if you looked at like super high delta super and like, you know, so super.
No, I mean, like this island could be not a like single point, but a collection of points.
Sure, okay. There's another question of like how small is the island? Well, so in the next lecture, I'll kind of show a video kind of showing how the Ising model island is getting smaller and smaller. So it's incredibly small at this point. I mean, it's like 20 digits small. And so I don't know if it'll ever shrink to a point. That's kind of a conceptual question. I doubt that will happen, because after all, we're just looking at a finite number of constraints. But it's so small that I think most people would say this is probably approaching. Okay, so any other questions?
Did people try to study one-dimensional CFTs?
People have studied one-dimensional CFTs. Yeah, so I mean.
No, I meant like find it using bootstrap. SSYK, something else.
So people have done numerical bootstrap for 1D CFTs, but that's usually in the context of defect CFT. Because it's like.
I want precisely nice one-dimensional CFT, not like.
Or is it with a stress tensor?
With a stress tensor, like SYK.
Yeah, but I think I don't know if you have non-trivial examples of that. So like, I mean, like SYK doesn't exactly have conformal symmetry, you know, it's kind of like programming. And so like, I think it's even probably some theorem that like, if you have a stress tensor and you're in one dimension, then the CFT maybe has to be true.
I mean, like, no, I want to state like n equal to infinity.
Seeing like the O infinity model in one dimension.
Yes.
See, but not as a defect CFT, just as a proper CFT with a stress tensor. I mean, I'm not sure it exists. I mean, like, I think like, no, but the SYK model is not, it's not a CFT though. Well, because it breaks conformal symmetry. Well, I thought the whole point of SYK model, I mean, that's
just
like
because exponentially small gaps at finite time.
Sure, but I'm saying, but like it does explicitly break. I mean, it's like, I mean, that's why it's dual to not ADS2, but like near ADS2. You know, like nearly ADS2, because the idea is that it breaks conformal symmetry explicitly, but like in some controlled way. You know, and so like there's like a certain mode of SYK, which is like dual, I guess, to the broken conformal symmetry, but there's other modes which are not captured by conformal symmetry.
It means that it's
Anyways, okay, so I guess that's that. Turn off this thing.